not inhibiting entirely. So first of all, we are not inhibiting protein synthesis, but what we're doing is we're inhibiting an inhibition, right? So the pathway has to be on in order for the drug to affect anything. So if the stress pathway is not on, it doesn't do anything. The second part of this is that if you cannot do the signaling through the pathway, which we can test genetically, for example, by just blocking this phosphorylation event I mentioned, then the mice are embryonically lethal. So these pathways are required to function. And what we're doing here is we are affecting a very subtle difference in where the dose-response curves are affected in such a way that we actually have incremental. So basically, in the heterozygous mouse that shows this better learning behavior in the genetic models, we only make half as much of the inhibitor. What we find is that if we have a lot of phosphorylation going on, this pathway is still protective. So I think you can do it both ways. We can still keep the protection at high reduction of the pathways, but what we're doing is we're modulating it in the middle range of the concentration of the inhibitor. There's a lot to be learned, and I think it's in the dose of the response that is being affected here.
Okay, very good. Let's move to you again. First of all, I'd like to congratulate all the laureates. It's a distinctive privilege for me to be addressing such a distinguished audience. So today I'd like to talk to you a little bit about statistics and challenges in a data-driven scientific world. Galileo famously said that the laws of nature are expressed in the language of mathematics, and that's certainly true. And the development of mathematics has gone hand in hand with the development of physics for centuries, and this happy marriage continues to this day. And to some extent, that's what this prize recognizes as well. But I think in the 20th century, which was termed the statistical century by my colleague Brad Efron, we saw the eruption of a new science, namely statistical science, that extends considerably the range of quantitative reasoning, not only within the physical sciences, but to new sciences, such as the life and medical sciences, the social sciences, economics, and so on. And so in all these fields, we have theories, and these theories can make predictions, and it is important to test the predictions against carefully collected data. Now, the thing about statistics is that sometimes these experiments, the experiments you do to test theories, do not yield a black and white answer, a 0-1 answer, but rather you have to deal with uncertainty. And statistics is precisely the language that lets you address uncertainty and evaluate the strengths of a scientific theory against data. Now, this way of thinking has been extremely successful. I chose to emphasize an early success of statistical thinking. The Saul-Braxton trial from 1954 aimed to eradicate polio in the United States. And what I'd like to emphasize here is statistics was not important only for analyzing data. It was, but also for designing the experiment itself. How are we going to compare children that receive the treatment, the vaccine, from those who do not receive the vaccine? And so this has been enormously successful, and so with enormous policy implications. And so now, of course, all these techniques have been perfected over a half a century, and now we have a rigorous process of clinical trials that bring drug to markets, which, to the best of my knowledge, do not harm people, but rather help them. Fast forward to 2017, has something gone wrong? I'm sure you're all aware of a lot of scientific and media attention in an enormous problem that seems to plague scientific research at the moment, which is the lack of replicability. You see on my slide the cover of The Economist from a few years back. And so we see a lot of issues raised around the fact that science is a thing that should replicate itself, but it seems to replicate less and less. So perhaps you've heard about claims in the field of psychology and things like this, but it also affects the life sciences. And so there was a very influential paper published in Nature in 2012 by Bigley and Ellis that reported that, for example, among others, Amgen, which is a biotech company located in Southern California, what they've done is they took 53 studies that they considered to be absolutely landmark in basic cancer science, and they set out to reproduce them. But to their surprise, they could only reproduce 6 of the findings. And so there's a German equivalent who will try to reproduce things with very similar results. So this is gaining enormous attention. Nature, Science, all the top journals are concerned with this. We see a lot of articles in the popular press about this, and that cannot certainly boost the public confidence in scientists and in science in general. So we have this crisis. Why is it happening? Well, there are many factors underlying the replicability crisis. For example, perhaps the publishing culture is at fault. Perhaps the granting agency culture is at fault that requires the researchers to claim extraordinary results before getting funding, and so on. And so, of course, all of these factors are well above my pay grade. But I think what I would like to emphasize is the statistical component of the replicability crisis. I think it is not a coincidence that we have problems with replicability precisely at the time where we're suddenly able to collect massive amounts of data. So as you all know, in the heart of the Silicon Valley, we collect more and more data, and everybody wants to use this trove of information to improve their business or their science. But I think what happens with this is that now we have large data sets available prior to the collection the formulation of scientific hypotheses. And so if you think about this for a second, what we've done is we've turned the scientific method upside down. Before we were formulating hypotheses, let's say, take the example of genomics, about a single gene, and we would carefully design experiments to test the function of this gene. But now, because of technological revolutions, we can measure the expression profiles of tens of thousands of genes at the same time, and we'd like to understand which one are in the pathway of some disease. So we've turned the scientific method upside down, and so now we have to develop new scientific and statistical tools to address this new paradigm, where essentially we collect data before asking questions. In other words, we're going to look at a lot of data sets to formulate hypotheses and validate them on the fly. And there's nothing wrong with this, but we have to be careful with what we're doing. So what is an example of a purely data-driven question? Well, that's kind of what supported the initiative around the Human Genome Project. Here's an example of a data-driven problem. So I have a response Y, let's say it's a phenotype, and it's whether I have some disease or not, or my amount of cholesterol, and so on. And now, because of technology, what I can do is I can measure thousands and thousands of things about me. For example, it has become extremely cheap to genotype an individual. And so I can measure lots of genetic information about you. So the problem that we face now as scientists is this: which genetic variations influence a trait, the risk of getting a disease? That's the question we need to answer. There are many questions in the data-driven science that we have like this. For example, and it was featured in the previous talk, we can monitor the gene expression profiles of many genes at the same time. We'd like to understand which one helped me determine the severity of a tumor. Or moving away from the life sciences, and something that I think, as you understand, in this AI-dominated world becomes more important, I might be interested in understanding which factors or variables determine whether a loan will be repaid or not. So in all of these examples, what we have is we have a response of interest that we would like to understand. We have lots of what statisticians call covariates, lots of variables potentially associated with this response, and I would like to select as many of these variables as possible without too many false positives, because I am not interested in going to a biologist and reporting a set of genetic mutations that has nothing to do with the problem I'm looking at. I do not want to run into the problem of reproducibility. So if I want to formalize the selection problem a little bit, then we can imagine that, for example, taking my genetic example, that we have a sample of people, and they come both with a phenotype and their genotype. And so I have an X and a Y, and I'm interested in predicting the Y. And so my task as a statistician is to predict whether a given genetic mutation will cause, or maybe cause is a big word, but will change the distribution of the response, the likelihood of me getting a disease. One thing we can formalize is I can measure millions of things. I can measure millions of mutations. I'm asking which of these mutations truly change the distribution of the response. So mathematically, you can think about this like this. I have a response, whether I have a disease or not. I have hundreds of thousands of mutations. I'm looking at one mutation. I want to understand whether the distribution of the response changes, whether I condition on this variable or not. That is, if you look at what's on the slide, is I want to understand whether this mutation provides information, additional information about the disease status beyond what the other variables already offer. Okay, so that's a tough problem, which is very different from what statisticians have looked at for many years. And so just to kind of explain a bit why this is delicate, we have now a lot of tools that can measure the strengths of dependence. We live in the computer age, where tools are extremely complex and sophisticated, and so we can use them to actually tease out which variables are important and which are not. But they're so complex that we should use them as black box. And so to give you a sense of like how a data set might look like, here we have a phenomenon that we're looking at. We have 500 possible variables, and so I have this black box that gives scores to each variable. Hopefully a high score measures an important variable, and so I get a plot like this, right? So I get a lot of scores, and so now I can hold everything the same, the statistical model is the same, but I just change the sample. But I'm looking at the same phenomenon. And so I get a plot like this now. And if I change the sample, I get a plot like this. And if I change it more time, I change like this and like this. So you see I have enormous variability that I need to account for. See, science used to be about distinguishing signal from noise for a single event. But now we have extremely noisy estimates about lots of things because we're looking everywhere at the same time. And so how are we going to do this? Because in what I found on the web, sorry. So Siri seems to like what I say. Okay. And so we have only one experiment, and so we have to decide what to select. And so we have to select in the face of tremendous statistical variability that is fully understood because we use this extremely complex black box. Okay. So one method to think about this is a method of knot box that we have introduced with the former spokesdog, Rina Barber. And the idea is it's very straightforward. Like for each variable, for each real genetic mutation, I may want to introduce a fake mutation. And the idea of introducing a fake mutation is to try to create some sort of a control group that I'm going to use as knockoffs. And so the idea of this method is to try to, how do I go back? Okay, all right. Okay, so the idea of this method is to actually feed the black box with both the real variables and the fake, and to look at what the black box does on the fake data set to sort of infer what it's doing on the correct data set. So now one way to actually introduce a fake data set is by what statisticians would call a permutation method. That is, I could try to append to my genetic information a new genome that has no relationship with the response whatsoever, because I could just impute the genome of someone else, hence breaking the relationship between the association between the phenotype and the response, and perhaps use someone else's genome as a control. But that method does not work. So what you see on the slide is a plot of feeding the black box with both the true genomes and genomes from random individuals, and measuring the scores given by the black box. The red dots indicate variables that I have truly predictive power, and the blue dots are those dots that do not have any relationship with the truth whatsoever. And so just focusing on the blue dots of false discovery, so to speak, I can see that by just using this needle permutation method, this naive idea does not solve the problem. Okay, the distribution of the scores associated that I get by imputing a random genome does not look like what it needs to do. Instead, if I use these knockoffs, which are constructed in a very specific way, then we get a picture that looks like this. And so then I can see that the distribution of the fake scores seem to mimic the distribution of the null scores, those scores that have no relationship with the ground truth whatsoever. So it works, and not only works, but it provably works. In fact, you can use these ideas to build a complete wrapper around the black box. That is, you can feed real data and these fake data that are carefully constructed, such that you can look at what the black box does on those types of variables and select variables with guarantees of reproducibility. Now, there's a lot of stuff, of course, I'm not saying. When I discuss these things, how you make them, how you select. Here, I'll just say one thing, is I want to kind of convince you that statistical reasoning is extremely important, and that also this requires a lot of sophisticated mathematical ideas. So the correct statistical reasoning and correct mathematical reasonings are crucially important. So one of the things in the last 2 minutes, do I still have 2 minutes? In the last 2 minutes, I would like to broaden the subject a little bit, because I think I want to make a claim which is a bit grander than just being a pure scientist and addressing this issue of reproducibility, and talk about perhaps other contemporary issues. So, and obviously science is about establishing causality. And clearly, if we knew how to do this from observational data, then I think this reproducibility problem would go away. But I think that by focusing on reproducibility, by paying attention to what's being truly selected and is it replicable in the face of enormous statistical variability, it is a step toward causality. And in fact, this can be made extremely precise in perhaps simpler models, where to actually go through the program I just outlined, we'll actually discover causal variance. So this is a two-way street. But at the same time, we're on the heart of the Silicon Valley, and as you all know the power of AI systems, and everything is about prediction. And so what we've learned is that to be able to predict well, we don't need a mechanistic model. But one way is not to have a purely mechanistic model, another is to have a model that pays no attention whatsoever to relationships that might be causal. So we can argue that if we keep an eye towards causality, by selecting important variables, we can perhaps improve those algorithms whose only goal is to predict, by perhaps making them more robust and more fair. So I would like to hit on these last 2 points. The first is robustness. So you see a lot of articles, this isn't one published in the Proceedings of the National Academy of Science, that claim that, well, if you like curly fries, it's very helpful to predict your IQ, and that may be true. That may be true in this very particular sense. Some true in that location in time and in space. And maybe true outside, I don't know. But the goal of predictive algorithm should not just be to be able to predict what's happening on this data set. But we want to be able to retain predictive power in circumstances that are a bit different. How about tomorrow? How about in a different city? How about in a slightly different population? We would like to be able to have predictive power which holds under varied circumstances. And that's really what causality is about. Causality is what remains invariant through different circumstances. So perhaps by focusing on causality and focusing on variables that are truly important, we can improve the robustness of predictive algorithms. My second point, which I think is extremely important, is the fairness of AI systems. Perhaps you're aware that Microsoft put out an AI robot named Tay that very quickly learned to become racist and sexist. AI systems work and use data that may contain many biases and that do not include any sort of causal relationships. As a result, perhaps there was this famous story, there was this famous Harvard professor, Anya Sweeney, she Googled herself. And as soon as she Googled herself, there was an ad saying, Anya Sweeney arrested ? Asking her to run a background check. Similarly, when women look for jobs, they tend to be presented with lower paying jobs, reflecting biases and prejudice. These biases and prejudices are not causal. And so there's a great danger in learning from data to just verify those prejudices and biases and to make them the norm. And so we have to fight this back. And then by focusing on what's truly causal, my claim is that it may help address this problem and not verify prejudice and biases. So the next 10 years, well, we have lots of work on our plate. What I want to convince you is that learning from data is not trivial. It requires an intellect, and it requires a lot of mathematics and a lot of quick statistical reasoning, and these things are very subtle. Thank you very much. Wonderful. Thank you, Emmanuel. Questions? Oh, right there in the back.
That was a great talk, thank you. I was wondering if you could speak on the dummy variable method that you created. Do you think it's feasible to create a metric that generates these variables in a more agnostic manner, that you don't need a lot of domain expertise in GWAS, for example, and reply equally well to an RNA-seq dataset, or is it inherently going to require a real amount of tailoring to get these types of approaches to work?
Yeah, I think it's a very good question. At the moment, we know how to do this in a few specific applications, but it's true that we do not have a general recipe. So what is required of the method is to know something about the distribution of the covariates. Sometimes we have a lot of unlabeled data that we can use to learn this distribution, and that is a situation where the method could be deployed effectively. But when I have no idea about how the variables are jointly distributed, it's unclear a priori how I would do this thing. And so it's a question for open research. Right here. So can you have the microphone right there? Please raise your arm again. Thanks.
Thank you. I'd like to know, do you think the lack of replicability is due to lack of understanding of causality?
No, it's just like what happens.
Second question. That's the first part. Second part is once I have a good understanding of causality, the Bayes and inference network will be a good method to really handle these causality problems.
Thank you. the lack of replicability comes from the fact that people are given data sets that do not really have a specific theories to test, and they're going to try a lot of different models until something seems to work out. That's where the lack of reproducibility comes in. The fact that we're looking at everything at the same time, and we're not taking into account the universe of scientific hypotheses that we're testing at the same time when we report findings. But we're not correcting for what I would call a selection bias, and that seems to be the major obstacle. As far as the second component of the question about Bayesian, well, it's possible that it's, of course, there are Bayesian methods that are advocated to I'm not exactly sure how it is with causality, but to try to adjust for the selection effect. I'm not by any means trying to diminish their importance.
Good question right here.
Yeah, thanks for the talk. One question was around the first point that you made, which is basically a restating of the maxim that correlation not equal to causation. And then my second question was around whether the irreproducibility is often the issue with the effort that goes into collecting the raw data in the first place, in that if there are variations in the way the raw data is collected, then of course it's going to show up in downstream processes.
Well, I teach undergraduate statistics. I absolutely fully on board with you. Causality is not correlations. That's what I tried to explain in the last part of the talk, where it seems that a lot of AI systems are just picking up correlations, but they may not have structural causal relationships. And so that's why I feel that they're perhaps reifying our biases and prejudice. And I think causality is a very hard thing to establish. And historically, we've relied on randomized double-blind experiments. But now I think it's important to try to make progress towards causality in the face of the enormous trove of observational data that we have. And to keep an eye towards causality when you select a model, when you feed a model, it seems to me to be a good principle. To examine the variables that you've selected, see whether they reflect close associations or not, seems to me like a good principle.
Very good. Do we have time for one more question? Oh, Professor, yeah.
You know, life sciences right now, or biomedical sciences, a lot of people are arguing that if you look at single cells, you'll reduce the background noise, and then you should be able to get at some of these issues. Do you think that's right, though? Because you can't really ever repeat the experiment, right?
Right. So of course, what we need to do is we need to be able to assess, absolutely. I mean, science proceeds by following false leads sometimes. But what we don't want to do is we do not want to only follow false leads. And so to have a sense of the strengths of what you're looking at in the face of these ideas is what I'm advocating. So a lot of modern statistical research is about the following problem now. It's essentially, I'm looking at thousands and thousands of genes, and I would like to be able to select genes that are possibly implicated in a pathway in such a way that I would give a set of genes to this distinguished audience. Well, maybe you will not waste more than 90%, more than 10% of your time. 90% of what I'm giving you is, in fact, related to the respondent. 10% may not. We will never go around this. As you know, science is not black and white, and we'll never go around this uncertainty, but we can help reducing the amount of false leads that we're following, and money wasted in following false leads.
Very good. Let's make it another again.
Good morning. So I do want to address what's next, at least in my personal opinion, and these things are a matter of opinion. So just to remind you, the overall goal in cosmology is to determine the properties of the universe as a whole, the big picture properties. And most of what underlies our work in doing this is Einstein's theory of general relativity. That's our theory of gravity. When Einstein came up with this, he realized that with matter in the universe would be dynamic. And at the time, there was no evidence that the universe was dynamic. It seemed unchanging. And so he had to figure out a way out of that, and he invented an anti-gravity term that he called the cosmological constant, and he set the value of the anti-gravity equal to the value of the gravity, so the universe would be static. And so that was his solution. That was wrong. And Alexander Friedmann, several years later, used Einstein's equations to come up with what we now call the Friedmann equations, which allow for a much wider variety of possibilities of what the universe could do. But they provide a constrained interaction between the dynamics of the universe, expanding or contracting, the curvature of space, and the contents of the universe. So that's the fundamental theory that we build on. But to get any further about our universe, we need observations and data. And so that's the next step. And so the baby picture of the universe that
that was mentioned in the introduction is shown here from WMAP. This is the fluctuations in the very early universe, and the thing that we want to do is fit a model to these patterns in the sky and to learn more about the universe this way. The model that we fit is called lambda CDM. The lambda is the symbol for Einstein's cosmological constant. Since although he was wrong about why he introduced it, it seems to fit the data rather nicely, but not balancing it equally with the matter. So in fact, we can determine several properties of the universe by fitting these patterns, and this includes the fraction of the universe that's in atoms, the stuff that we're most familiar with, the fraction that's in this cold dark matter. It also has gravity, but it's fundamentally different from atoms in that it doesn't emit any light at all. So it's a different thing altogether, although it shares the property of gravity. We can also use this model to fit the current expansion rate of the universe. And then there are two parameters that have to do with the very earliest times, the amplitude of primordial fluctuations, and then there's a little bit of a tilt parameter to allow that amplitude to change with the size scale. And then finally, there's a parameter that talks about how much the cosmic microwave background that we study, traveling across the universe for 13.8 billion years, how likely it is to scatter on the way to us. So there's 6 parameters there that we get from fitting that map. Now, there's another kind of fit that we can do, too, which also constrains the curvature of the universe. That was one of the parameters I mentioned that's constrained. And so when we fit that, we find that the universe acts Euclidean, the sum of the angle of the triangle of 180 degrees. So we usually fix that and just work with the other parameters. And finally, there's one more parameter that people in my field often forget about. An earlier space mission I worked on called COBE, Cosmic Background Explorer, determined the temperature of this cosmic background radiation, and that it has a black body spectrum. And once you know that, you can estimate the energy density in radiation and in neutrinos, and you add all that together, and basically there's another parameter, which is the total energy density of the universe in radiation. So you can see, we always say there's 6 parameters, but if you count the curvature, maybe it's 7, and if you count the earlier data, maybe it's 8, which reminds me of the old joke that there are 3 kinds of cosmologists, those who know how to count and those who don't. So here's the result of what happens when we fit the data. We find that atoms are less than 5% of the universe. This cold dark matter that